Okay, hi everyone. Let's get started with today's lecture. In today's lecture, we're going to be talking about decision trees. So this is our second lecture on this topic, and by the end of today, we'll wrap up decision trees. So just a couple of announcements and reminders. The fourth homework is going to be released later today. It's a bit more of an involved homework than homework 3, so you're going to be doing a lot more sort of hands-on implementation in that assignment. It's going to be in 2 weeks, so Friday, May 26th. This fourth homework is all about decision trees, and actually after today's lecture, you should be able to do pretty much everything in the homework. So as always, I encourage you guys to start on that early. The second announcement and reminder here is that project team formation is due this Friday. About 103 students are still not in groups, so that's about 60% of the class. And this again is worth 10% of your project grade, just finding a group on time. So yeah, make sure you find a group by that deadline, free points. And as always, I encourage you guys to start working on these things sooner rather than later. Yeah, start thinking about this project. Maybe start plugging away at whatever data set you chose, because these are due in about 1 month. So yeah, just a reminder, projects exist in this class. Okay, so in today's lecture, we're going to see a recap of decision trees, just a reminder of how these work, go through the details about learning them. Then we'll see a pretty hands-on example of actually fitting a decision tree to data, so we'll step through that tree learning algorithm step by step and see how that works. And then at the very end, we'll see how you can actually implement decision trees in code, give you some previews and some hints for the homework. Okay, so a reminder of what a decision tree is. Let's say we have a really small data set consisting of binary features, x1 and x2, and binary labels. A decision tree is essentially some kind of Boolean function that we represent as a tree, where in every node we have one variable, one feature coming from our data set, and at every sort of branch here we make some Boolean decision about the value of that feature. So if x1 is 0, we'll go to the left in this tree. If x1 is 1, we'll go to the right in the tree. And eventually, by traversing this tree and reaching the leaf nodes at the end of our tree here, we can make some kind of classification decision for our data set. When we have features that are not binary valued, so not features taking zeros and ones, but rather real valued features, what we can do is take our real valued features and threshold them. So what I mean by that is I might take my first feature and say if x1 is larger than 0.5, I'll go to the right in my tree, and if x1 is smaller than 0.5, I'll go to the left in my tree. So visually on this 2D data set, this corresponds to this kind of horizontal, or rather vertical split here. We can do the same thing for the second feature. Then again, when we reach our leaf nodes, we make some kind of decision. Oftentimes, we don't want to just return a predicted label at the end of our decision tree at the leaf nodes, but rather we want to predict probabilities. So we've already seen a few times while these probabilities are useful, they can represent sort of uncertainty in our predictions, and we can use them to define multi-class classification models. But what we mean by returning probabilities is that we just count up essentially the number of relative frequency, rather, of classes appearing in these decision regions. So here, this region here corresponds to this node down here, and the probability that y equals 1 should be, in this case, 3/4 rather than 0.25, actually. So for multi-class classification problems, same exact idea works. We split up our data into sort of distinct regions based on thresholds on the features, and in the nodes we return a vector of probabilities, where for each leaf node, we return one probability per possible class. So for example, in this blue node down here, corresponding to this region down here, we might have probability of blue is 1, 2, 3, 4, 5, 6 out of 8, and probability of orange is 2 out of 8. Essentially, again, just counting up the relative frequencies of the labels in the corresponding regions. Okay, so we saw all this in the last lecture, just recapping how these work. Okay, so today we're going to go a little bit more slowly through how you actually learn decision trees, and we'll see some examples of how this works. The idea, again, is we're going to somehow construct or grow these trees in a top-down fashion. So we'll build a root node. That's our first split of our data set. We'll actually take our data and split it based on that root node, and then get two subsets of our data, split those subsets again, and just recurse. So in terms of some pseudocode that we saw last time, our input into our sort of build tree algorithm, which is what we're going to call it, is some data set D consisting of features X and labels Y. And the first step is that we're going to create a new node at every sort of call to this build tree function. At this node, we're going to compute a class probability vector, which again is just the relative frequencies of the labels in this data set D up here. If this new node that we created satisfies some leaf condition, then we're going to just call this node a leaf node and we're done. We don't need to do any additional splitting. If it's not going to be a leaf node, well then we need to take this node and split it. In order to do so, we're going to find the best possible split of this data set D we're considering at this particular node. After finding that best split, we're going to take our data set and actually perform this splitting. So we'll create a left data set and a right data set, which are subsets of this original D that we passed in, where we actually split the data based on this condition that we found. Our new node that we're creating in this step of the build tree algorithm will then get two children in the tree, where the left child and the right child are going to be essentially nodes that we then create from this left split and this right split, recursively calling this build tree function. So just staring at this code, it's a little bit black box what it's actually doing, and we'll see some examples in just a minute. Okay, so details that we left out in the previous sort of pseudocode are how you compute this class probability vector. Again, this is just the relative frequencies of the class labels we're looking at when we're constructing those nodes. So here's an example we saw last time. We're going to go a bit quickly through this. We also need to consider what sort of conditions on a node would lead to that node being considered a leaf. So typically, again, we do this if all the labels in that node we're considering are in the same class. Does it make sense to split the node in that case? We oftentimes also create a leaf node if we're at the maximum depth of a tree, again, making sure our trees don't grow too large. Or the number of examples we're considering at the current node is smaller than some minimal number of examples, again, preventing overfitting. We saw this number called the Gini index. And what this Gini index does is it takes in essentially a set of class labels or a set of probabilities and computes their variance. So if I'm given a set of probabilities, one for each possible class in my data set, the Gini index corresponding to this set of class probabilities is just 1 minus the sum of their squares. So again, this is the variance of those sort of probabilities. And the way we use this Gini index is that when we're considering a new node, so we're trying to make a new node in our tree, if we're looking at a particular feature and a particular threshold for this feature, we compute the Gini index as follows, where we split our data based on this feature we're considering into a left subset and a right subset. We compute the fraction of data points going to the left and the fraction of data points that are going to the right. These are PL and PR. We compute the Gini index on the left data set and the right data set, using that formula from the previous slide, and then compute a weighted average of these two, using PL and PR as my weights. So in this way, I take sort of a proposed split, i.e. a feature and a threshold, and I compute a single number, this Gini score, based on this proposed split. And then whatever split that I have in my data set that minimizes this Gini score, it's going to be the best possible split that I can perform on my data set. So in other words, given a subset of data D that we're considering at a current node in our tree, we compute the Gini index of every possible split of this data set D. So we look at every feature in our data set and every possible threshold of this feature, compute this corresponding Gini index for this feature pair tuple, and our best split that we can do at this current node we're considering is whichever feature and threshold tuple resulted in the lowest Gini index. Good timing. Yes, it is. Well, no, it's not a separate class, it's a separate feature. Maybe let's look at an example, and hopefully it'll be clear what's going on after that. Yeah. Other questions? Cool. Yeah, let's look at an example, and I think things will be a lot more clear after we step through this. So let's say we just have a single feature here that we're considering. One thing we didn't talk about is how you decide what threshold values you should evaluate when you're trying to decide how to split this feature. So one thing to note is that the Gini index really only counts up how many labels are occurring on either side of this sort of threshold. So it only depends on the number of labels to the sort of left of a threshold and to the right of a threshold. So we only need to evaluate thresholds sort of in between individual data points. So for example, if we're considering to split on this feature here, shown in one dimension, we only need to consider a threshold between these two data points, between these two data points, between these data points, and so on and so forth. So you can say pick thresholds that fall halfway between each of these data points. So we might visually be considering these various thresholds that we will then loop over. So in general, if we have n data points, and that means we're going to have n minus 1 thresholds to consider for every feature. So let's look at an example here. So we have two features in our data set, x1 and x2. These are real valued features here. What we're trying to do in this example to start out with is figure out what's going to be the root node in my decision tree. So what feature should I split on, and what threshold value should I split that feature on? What we have to do is look at both features and look over all possible thresholds, compute their Gini indexes, and then figure out which one is the minimum. Okay, so the Gini index, before doing any splitting in my data, so this is, before doing anything at all, is just 1 minus the sum of the squares of these probabilities. So the probability of the class red is 0.5, and the probability of the class blue is 0.5. So the Gini index before doing any splitting is 0.5. Okay, so let's first look at the feature x1 and consider all the possible thresholds and compute their corresponding Gini indexes. So the first threshold I need to consider is this threshold that's between my first data point, this blue point, and the second blue data point. It's the first threshold that's going to do any splitting of this first feature. If I put my threshold to the left of this first blue point, well, it's not splitting any of my data points, nothing's happening. And I choose this threshold to be at the feature 1.5 because my first data point is x1 equals 1, and my second data point has x1 equals 2. So I just choose the midpoint between these two feature values. My point on the previous slide with that sort of 1D example was that you can pick any threshold value between 1 and 2. It'll perform exactly the same splitting, but just for the sake of making things concrete, we'll choose this midpoint 1.5. So if I split my data set using this threshold, 1 out of my 12 data points goes to the left, it's this blue point, and 11 out of my 12 data points go to the right, it's all the remaining data points. The Gini index on the left is then 0 because, well, my class probabilities are 1 and 0, so if I just plug into the Gini index formula, I'll get a 0 on the left. And if I plug into the Gini index formula for the right, I'll get 0.496. If I take the weighted average of these two numbers using PL and PR, I'll get this value down here, 0.455. So I encourage you to kind of step through the math of how I get these numbers on your own, but you'll have to trust me that this is the actual Gini index of this split. So are there any questions on how I computed this value? Because what we're going to do now is just recurse. Yeah? Yeah, so the Gini index, let's go back to the formula for that real quick, is 1 minus the sum of the squared probabilities, where these probabilities are the relative frequencies of the labels in the split we're considering. So it's 1 minus sum of p squared. We have one probability for each of the classes in our data set. So let's jump forward to this example. On the left, we only have one data point that we're considering. So the probability of blue on the left is 1, and the probability of red on the left is 0. So it's going to be 1 minus 1 squared plus 0 squared, which is 0. Same exact thing for GR, except now. Exactly. So we take our original data set and make two new data sets out of it based on this threshold. We've got the left data set, this single blue point. We've got the right data set, all of the data points on the right. Yeah, so PL and PR are what fraction of my data gets split to the left and what fraction of my data gets split to the right. So one data point goes to the left and everything else goes to the right in this example. Yeah.
So essentially, we divide, like, for this is our determinant for like our weight, we divide our tree into over 2 by 2, right? Does that imply that this
Yeah, so if we stopped here, if we didn't do anything else, we would have a tree where the first node, the root node, is essentially asking, is x1 smaller than 1.5? So that would be our root node if we stopped here. And if we go to the left in that tree, we would predict blue. And if we go to the right in that tree, we would predict, well, whatever the majority is on this right-hand side. But we're going to eventually build our tree to be deeper than that, yeah. Okay, other questions on what I've done on this slide? Cool. So what I do next is I just move my threshold over by one data point now. So rather than splitting off just a single data point to the left, I'm going to split off these 2 data points to the left. I'm going to do the exact same thing. I change my threshold to 2.5 because it's immediately between this feature here and this data point here. Notice PL is now 2 over 12. I've got 2 data points to the left and everything else to the right. Gini index on the left is still 0. I only have blue data points to the left. Gini index on the right is 0.48 if you do the computation. And you'll get a Gini index of 0.4 by taking their weighted average. Okay, move my threshold over once again to say between these data points, get a new Gini index, move it over again, get another Gini index, so on and so forth. But here I'm putting a threshold between every possible sort of data point, so I should have something like 11 thresholds here. Okay, here I have a graph now, where on the x-axis is the threshold value that I'm considering, so what point am I splitting my data on? And on the y-axis, I have that corresponding Gini index. If I put all of my Gini indexes on a plot, well, we said we're looking for the minimum Gini index. Lower Gini means it's a better feature to split on. And we see that the minimum value occurs at t equals 8.5. This means that if I'm splitting on my first feature, the best threshold for that feature is going to be t equals 8.5. And that corresponds to this split right here. And this should make sense, right? It's a good split in the sense that it puts a bunch of red data points on the right and lots of blue data points on the left. So it's doing a pretty good job at sort of trying to classify our data. Okay, so we saw how to compute Gini indexes for every threshold for feature 1. What we need to do now is consider splitting on the second feature rather than just the first feature. So we repeat this procedure now, except instead of splitting on x1, we're going to split on x2. So we consider all the possible thresholds here, compute their Gini indexes in exactly the same way as we did before, and get a new graph, except now for feature 2. And in this graph for feature 2, our minimum Gini value is 0.44 at the threshold of t equals 6.5. What this means is that for the root node in our decision tree on this data set, we should split on the first feature at the threshold of t equals 8.5, because this is the minimum Gini index that we found. So in other words, the root node of my tree is going to be this node, whether x1 is greater than 8.5. And what we see is if we write down the actual sort of split corresponding to this node, if we go to the right in our decision tree, well, all of our data points are going to get classified as red points. So this should be a leaf node, right? There's no point in splitting this guy any further. But now we take our left subset of our data corresponding to x1 is smaller than 8.5. So we've got this subset of our data remaining. And we'd like to further split this by creating new nodes in our tree. So what we can do is essentially recurse this algorithm, just apply it again, except we don't look at the full data set, we only look at the data lying to the left of this split. Okay, so let's do the exact same thing, but again, only looking at that left subset of the data. We consider all the possible thresholds between the second feature and the first feature, make these same plots, and here we see that we should split on feature 2 at the threshold of t equals 0.6, again doing the exact same computations we did before, just on a new subset of our data. This is the best possible split of this left subset of our data, so we make a node here at x1 greater than 0.6, or rather 6, corresponding to this sort of horizontal split of my data. And you can see if we go to the right in my decision tree now, well, I'm perfectly classifying all of these blue points. It should be a leaf node, so I get this leaf node. And if I want to continue growing my tree, i.e. if I'm not at the maximum depth of my tree, I should go to the left here and sort of do this procedure recursively. Yeah, go ahead. Yes, should be. So typo here should be x2 greater than 6.
I have another question. Is it always going to be like your root is x1 and then the x2, and maybe the root node is
Yeah, so it's certainly, you can certainly repeat a feature in the tree. So your root node could be splitting on x1, and your child node here could also be splitting on x1. Because notice here, when we're doing these thresholds, we look at both the second feature, right? And we also look at the first feature and all the thresholds. So you can split on the same feature more than once, certainly.
How do you decide that?
It's because you look at every single feature and every single threshold when you're computing a new node. Yeah, another question.
So you already designed the website being read, even if it has one viewpoint, you copy that one viewpoint to your calculating next nodes?
So you're saying if my tree looks like this already,
Yes. There's like one viewpoint on the right section.
so I get a blue point over here.
Yes. You copy, but of course you're already passing the first one, so it's like right in class. But you're copying the next one. You have that blue data point, or you only take those down and actually the red piece?
So it depends exactly on what you would like to do in your tree. So if you have one additional blue data point on the right-hand side, well, you could choose to make this a leaf node and just return the probabilities of the classes, right? You could say, okay, I'm done splitting once I go in this region. Or if you would like to split both the left side of this and the right side of this further, well, you would consider essentially doing this procedure twice. You would create a new internal node for this left subset of the data, and you would create a new internal node for the right subset of this data. So you would essentially chop your data set along this vertical line, and then create two new subtrees for each of those splits.
Inside of you get red of like calculating, and then you look at the other two, and you want to split it up and down.
Mm-hmm.
Leave that node, that data point, you're just putting into that side.
No. So when you're splitting the left side here, you only consider the data that is to the left of that threshold. It's like you made an entirely new data set where you only consider these points when you're considering this new internal node. Yeah. Okay, other questions? Cool. So far we've seen an example of building decision trees where your features are real valued. Of course, we can extend decision trees to consider more general cases than just real valued features. So if you say have a binary feature, it's easy enough to add these into the sort of setup we've already been seeing. We only need one split to test, essentially. There's not multiple thresholds we need to consider. There's only sort of one value to test here. If you have categorical features in your data set, say corresponding to the state a person lives in, you can turn this into a collection of M binary features and just repeat this procedure we did for binary nodes. And there's no problem with comparing the Gini values between sort of binary and categorical nodes against those with real valued nodes. So really you can handle binary or categorical data in exactly the same fashion you would handle real valued data with a decision tree. Another thing to consider when you are constructing these decision trees is how you should select the size of these trees. One thing that's typically done in practice to sort of control the complexity of your classifier is to grow a very large tree to start out with, say something with a depth of 10 if you have a large enough data set, and then prune this tree back using a validation data set. So by pruning, what I mean is taking some of the leaf nodes in your tree, essentially chopping them off and making a leaf node a higher level up. There's various heuristics to do this. I'm going to skip over the details here. They're a little complicated. The idea is sort of the same thing we've always done for model selection, where we're going to use a validation set and assess the performance of our model on this validation set in order to determine, what's the best pruning of our tree. Other ways of controlling the tree size here are, say, setting a maximum depth, as we talked about, or setting a minimum number of examples in a particular leaf node. Okay, questions? We took a few earlier, so there might not be any at this point. Yeah. Yeah, exactly. I wish I had a good example here, but let's say you've got a leaf node here, and let's say you also put a leaf node over here. We can kind of combine these leaf nodes into a new leaf node one level up by just returning kind of the combined predicted probabilities from these leaf nodes. So it's a way of kind of reducing the complexity of your tree by kind of reducing the depth in sort of local places, if that makes sense. Okay, other questions? All right, let's look at a few examples of decision trees sort of in code and what these actually look like, and give you a few pointers on how you can get started actually implementing these in your homework. So for homework 4, in problem 3, you're going to be implementing this decision tree learning algorithm basically from scratch. So we give you some skeleton code to help you get started, and otherwise you're going to be filling in all the details. And hopefully this example we walk through is will help you sort of bug check your code, so you can actually put in those numbers in those data sets that I showed you, and you should get the same outputs that I got in lecture today. So the basic object in any tree, of course, is a node object. And so we give you this class, which I call node, and each node has various attributes associated with it. So my node here has depth, which is just how far down in the tree I am. We'll use depth equals 0 to represent a root node, so just convention here. In the homework, you'll only be considering real valued features, so every node also has some threshold, as well as some split feature. And by split feature, what I really mean here is what's the index of the feature that I'm splitting on. So if I'm splitting on the first feature in my data set, this split feature is going to be the integer just 0. So it's which feature I'm splitting on and what threshold I'm splitting it at. Every tree, or every node in my tree can potentially have children, right? So I might have more nodes coming after it if it's not a leaf node. And so left child and right child will also be node objects corresponding to just the next level in my tree. And then by probs, I mean a NumPy array representing the class probabilities at that particular node. So it's going to be a length 2 NumPy array containing the probability that y equals 0 and the probability that y equals 1 at this node. To keep things simple, we're only considering binary classification here, but more generally, this probs could be a longer vector containing k class probabilities if you've got multiple classes. And here we've just got a nice representation of our nodes, so you can print them out and look and see what they look like. So we give you this code, but it's good to understand what this is actually doing because you'll need to use these in your implementation. Okay, and then we've got this build tree algorithm. Here I'm just showing you a snippet of it because basically everything else is blank and you guys will have to go in and actually fill it out yourselves. But I've tried to write this such that it follows that pseudocode that I've shown you guys a few times pretty closely. Again, the idea is that every time we call this build tree function, we pass in a data set consisting of a collection of features x and a collection of labels y. And we'll also pass in the depth because we're going to use this later on. But every time we call this build tree function, we're going to create a new node at our depth that we're currently considering. So I make this new node object. If the depth is 0, then the root of my tree is this new node that I've just created. I'm going to then compute the class probabilities for this node. So far, in the examples, I've really only shown you computing the class probabilities at the leaf nodes, but it's going to be useful for us if we can compute these class probabilities at every internal node as well. So I take in some collection of labels y, and I just need to compute essentially what's the relative frequency of the label y equals 0 to the label y equals 1 in that collection y. If this new node that I've created is a leaf node, by checking some leaf condition, which you guys are going to implement by yourselves, well, I don't need to do any further splitting. I can just return this node that I'm currently looking at. Otherwise, I need to take this node, because it's not a leaf node, and now split it into a left and a right node. In order to do so, I need to find the best split. So you guys will implement this find best split function, which again just takes in a data set corresponding to features and labels and does this procedure that we walked through today. This find best split function should return a split index. So which feature should we split on? And here it's just an integer corresponding to the index, as well as a corresponding threshold. Then you need to actually split your data set into a left subset and a right subset, and then create new nodes in our decision tree corresponding to that left subset and that right subset. And at the end of the day, we need to fill in sort of the children and the split feature in the threshold of our node. So just some bookkeeping at the end. So in all, not too bad once you implement each of these pieces here to get a decision tree implemented in code. Somewhat interestingly, we saw how to implement a neural network in code, right? And it was, roughly as complex as implementing a decision tree, maybe even less so because, we didn't have to worry about this recursion. And This is despite the fact that neural networks, so much more complex than a decision tree. So it just goes to show that, lines of code is not a good measure of complexity. I'll also show you some code here, just walking through how you make predictions with the decision tree. So we give you this code, no need to worry about implementing this. But again, the basic idea of how you predict a label given a decision tree after you've learned it is you just traverse this tree until you hit a leaf node. So at the start, or the current node we're looking at is the root node, and then we just have a while loop. If we're at a leaf node, we'll return the predicted probabilities. Otherwise, we're going to essentially either go left in my tree or go right in my tree. So any questions on the sort of skeleton code we've walked through so far? Cool. I'm sure there will be plenty of questions on Ed once you start trying to fill this out yourself. So in terms of scikit-learn, which is, again, this ML package you guys are all pretty familiar with at this point, there is a decision tree classifier implemented, and you'll be experimenting with this a little bit in the homework as well. The most important kind of parameters here that you can play with are the criterion. And by criterion, we mean what's the function we're using to score a split. So in the lecture, we've only seen this Gini index, which again computes the variance of the essentially label probabilities. But there are other ways we could score splits when we're deciding whether or not to sort of add them to our tree. So we might look at something like entropy, which we didn't go over, or even something like the cross entropy, i.e. this log loss. So there's other choices for the scoring function that you can play around with, and is essentially a hyperparameter of your model that you can tune. We've talked about the maximum depth, so this is how big of a tree we're allowed to grow before we have to stop. Again, this is another important hyperparameter of your model, essentially controlling how complex your decision tree can be. And then we've got min samples leaf, which again we also introduced sort of conceptually, controlling, again, the complexity of our tree. Okay, so here's an actual example of a decision tree that I fit to some data. So here we've got a fairly complex data set where our blue class is sort of this blob in the center, and our red class is the ring on the outside here. What I've done is I've taken a decision tree in scikit-learn, and I've varied the maximum tree depth. So on the x-axis, I've got the maximum depth allowed in my tree. And on the y-axis, I have the error rate, just 1 minus the classification accuracy. So what you should notice is that the training error, this red line, just steadily decreases as I increase the maximum tree depth. This should make sense. A deeper tree means a more complex tree. It can fit significantly more complex decision boundaries. And in fact, if we make our tree deep enough, we should get perfect accuracy on our training data. We can make our tree so complex that every data point essentially gets its own little box, own little decision region. In contrast, the testing error decreases up to a certain maximum depth, but then starts to generally increase afterwards. So in other words, to the left of this maximum depth of 4, we're underfitting in the sense that our training error is decreasing, and our testing error is also still decreasing. So we could benefit from a more complex model because it's reducing our testing error. After this maximum depth of 4, we're now in an overfitting regime. Our model is great on the training data, it gets almost perfect accuracy, but the testing error is starting to increase, indicating that, again, we're overfitting to the training data. We're essentially memorizing the data points we saw and not able to generalize to new data points. This, of course, is an example of this general error complexity trade-off that we've seen so many times for so many different models, where, again, the idea is your model is too simple, it can't fit the training data in the first place, versus your model being too complex, it's fitting the training data too well. So as always, there's important parameters to tune in these models sort of before even fitting them in order to get good performance. Okay, let's take a look at a couple of real-world data sets here and just look at what decision trees look like. So we saw a little while ago this penguin data set, where we've got 3 classes of penguins corresponding to their species. So we've got Adelaide penguins, chinstrap penguins, and gentoo penguins. And here I'm showing scatter plots of the various features. So we can see, maybe looking at this scatter plot, that a decision tree might do pretty good here. We might want to split our data along this axis first, and then maybe along this axis, and we can, probably do pretty good here with a simple decision tree model. So I went ahead and fit a decision tree on this penguin data set, and I specified a maximum depth of 2 just to make sure my tree didn't get too complex. And if you actually go ahead and print out a decision tree in scikit-learn, it'll give you this pretty nice visualization of the tree. where the first line here tells you what feature you're splitting on and the threshold value. So the root node in my tree, it says I'm splitting on the feature x2 with threshold 206. It also tells me the Gini index at that current node, so sort of what's the variance in the labels of that current node, and it tells you essentially the class probability vector. Notice here it's not actually returning the class probability vector, it's returning the counts of the classes, but we could turn this into a probability vector by just dividing by their sum. So this value here is this thing that I've been calling probability vector in the lectures. We then have internal nodes corresponding to the first feature x0, the second feature x1, and again the same additional details. And then eventually when we reach a depth of 2 in our tree, we all have leaf nodes because my maximum depth here was 2. Okay, let's look at what this decision tree actually looks like in terms of the features that I have. So this first node here, again, was splitting the second feature, x2, at a value of 206. So my feature x2 is this flipper length, so I can draw sort of a split here corresponding to flipper length. And notice this is a pretty good split, right? It gets most of the green data points to the right-hand side of this split. And the reason I'm drawing this split in this kind of strange way is because, well, we have 4 features and we can't really visualize a 4D data space very well, so this is the best we've got. Let's go to the left in our tree, say. Here we're splitting on the feature x0, which corresponds to drawing this sort of split in my data. And again, you can see it's doing a good job of separating out the blue and the orange classes. If we instead go to the right in my tree, I would split not on the feature x0, but on the feature x1. So it's this bill length feature here. And again, it's doing a pretty good job of splitting off the green data points here. So this is just an example of showing what a decision tree looks like on some real data. Decision trees, even though they're a really simple model, are actually quite popular, particularly in applications to things like the sciences. So a cool place that decision trees have been used in the past are in astronomy. These are really useful because you might have, a telescope somewhere out in some mountain in Hawaii somewhere, taking billions and billions of images of various sky objects. And the problem is, we can't actually have astronomers sit down and classify all of these images. There's just way too much data. So astronomers have used decision trees to kind of build automated galaxy kind of taggers, if you like. So for example, here's a couple of different classes of galaxy images. We've got, say, spiral galaxies. We've got peculiar galaxies. I like how astronomers name these, peculiar tadpole galaxies. But you can actually take, say, a small subset of labeled data, say 50,000 images, which, you can pay some astronomy grad student to sit down and actually label these. And using this small labeled data set, build a decision tree that will then help you label, your huge data set of billions and billions of images. So this, again, is just to point out that these decision trees actually get used in the real world on some real problems. Another example of where these decision trees actually crop up is in medical applications. And so in medical applications, decision trees are particularly nice because we can actually interpret the nodes in a decision tree. So for instance, here is the root node in some decision tree in my medical task. And here I'm trying to predict whether or not a patient who has come into the hospital is going to be leaving the hospital. So if we go to the left in this decision tree, the first feature we're splitting on is this Glasgow feature. And I believe this is a coma indicator, basically. So if we go to the left in our decision tree, our patient has a pretty bad coma, and there's a 76% chance that they're not waking up from that coma. But if we split on the right, say they don't have such a bad coma, maybe they're conscious, we can split on whether or not they got some kind of treatment. Here it's some kind of inotropic treatment. I don't know anything about medicine. And then we split on age and so on and so forth. But my point here is that in each of these nodes, the features we're splitting on are highly interpretable, right? We can basically say something, whether or not our patient is over a certain age, what their mortality rate is going to be like. And this is really important for medical practitioners because, well, your doctor doesn't want to just take some patient records, stick them into a neural network, and trust the prediction coming from a network, right? How would we possibly, trust a neural network with your life? You have no idea what it's doing internally. In contrast, in a decision tree, you can actually show a graph like this to a doctor, and they can say, okay, well, no, I think you should split on 4 instead of 5 for this coma index based on sort of my clinical experience. So they're highly interpretable and can often lead to sort of insights about your data set beyond just a sort of big black box prediction algorithm. Yeah, question?
I think the first question was, in this example, it's like an easy interpret how the model is straight. But if you go to the previous example with the galaxies, for example, right? What is it splitting like?
In this case, I believe the features are handcrafted features extracted from these images. So I believe what happened is we had some astronomers sit down and write essentially feature extractors from these images. So you can take an image, pass it through a little bit of code, and it'll spit out some real valued feature. Here, this first one is some brightness or magnitudes or something like that. So these are features coming from the images that have actual like interpretable characteristics to these practitioners. Yeah, you wouldn't want to split on pixels or something like that. That wouldn't be very smart, yeah. Yeah, another question. Yeah, for sure.
So, for example, if you look at 30.7%, would that mean that all patients have a 30.7% of die or something?
Something like that. Please try again.
Don't worry, I got the question. No need to repeat it. Yeah, so this indicates that in this data set, 30% of the patients we're looking at didn't make it out of the hospital. So this is not saying 30% of all patients. This is probably being applied to patients in a coma, given this first feature here. I forget the exact details, but yeah, that's what the number is saying.
So it's basically saying, okay, 30% are probably going to be in the hospital, and then of that 30%, if they have Glasgow underneath or less than or equal to 5, then of the 30%, there's going to be 76%. That's definitely going to stay.
Exactly, yeah. So yeah, notice that if we just look at our patients and we don't do any splitting and just try and predict, okay, random patient comes in, what's the probability that they die in the hospital? 30%. But if I split on just this first feature, well, these numbers get a lot more specific now, right? If they have this Glasgow scale less than 5, well then 76% of my patients are going to die in the hospital. So I get a lot more specificity by sort of subgrouping my patients, and that's exactly what this decision tree is doing. Yeah. Yeah, other questions? Okay, cool. So let's wrap up with decision trees. We'll probably finish a few minutes early today. But I'd like to just kind of go over what are the relative strengths and weaknesses of decision trees. So we've seen lots of models at this point, and why would you use a decision tree over other models? And really the main strength of these decision trees, as I was emphasizing, is that they're really easy to interpret. They kind of have rules, almost if statements built into them. So they're very easy to kind of crack open and look at. This, of course, comes with the caveat that if you have a massive tree with like 1,000 nodes in it, well, good luck interpreting it. But this at least holds for small trees. Another benefit of a decision tree classifier is you can easily handle categorical and binary value features in the same framework that you would handle real value features. So no matter what data we have, we can stick it into a tree and it'll work basically the same. Another benefit is that it's kind of scale invariant for real valued features. What I mean by this is that we've seen on a lot of data sets that scaling your data such that your features are all on the same scale is really important. So something like a logistic classifier or like nearest centroids, you basically always want to rescale your data before fitting that classifier. But for a decision tree, because we decide on these thresholds when we're fitting the algorithm, there's no need to scale the data. It essentially would have no effect on the tree that we learn. So no need to scale for a decision tree. In terms of weaknesses, well, all of our decision boundaries, all of our splits, are necessarily parallel to the axes in our data space. This is just because we're only considering a single feature at a time when we're deciding how to create those splits. So our model has sort of high bias in terms of this bias variance trade-off. It's not as flexible as other models in the decision boundaries it can represent. These decision trees are also high variance in the sense that a small change in your data set can lead to a large change in your tree. So if a different root node is selected in your tree just because you get a slightly different data set by chance, well, the tree that you learn can be quite different than if you had a very similar data set. So even a difference of one data point in your data set can lead to vastly different trees. They're very sensitive to this kinds of stuff. Okay, so to summarize, decision tree classifiers have a very flexible model, but are limited to sort of axis parallel or linear decision boundaries. But if you make them deep enough, they can represent almost arbitrary decision boundaries. Of course, this comes at the cost of then having a model that's likely to be overfitting. And the idea is we construct these trees such that at each internal node, we split on a single variable at some threshold that we choose. And at the leaves of our decision tree, we're producing probabilities corresponding to each class in our data set. In terms of learning decision trees, we saw lots of examples today. So for each node we're creating, we score every possible split and pick the best used, say using the Gini index or some other criterion. And of course, the complexity of our model, sort of this overfitting, underfitting idea, is controlled by the number of nodes in our tree and the depth of our tree. And as promised, we're ending a little bit early, so if you guys have additional questions, we can take those now or after lecture. Okay, that's all guys, thanks.